The question is, could you do an example on calculating V and M at a point in a beam? V here is the shear force and M is the bending moment. I have chosen this problem here. This is a fairly comprehensive beam problem involving various things, including a point load, a concentrated moment, and a distributed load. Also, one has to be especially careful about calculating the internal forces below a point load, concentrated moment, or at a point within a distributed load. So I have intentionally chosen those points here. First step is to find the support reactions. If you recall from one of the previous videos, depending on the problem, sometimes we don't need to find all of the support reactions, because in the next step, we're going to section the beam and consider only one side in the analysis. We only need to develop the free body diagram for that side. However, having all of the support reactions would allow us to check our answers, right? So I have found all of the support reactions here. Since at this stage you are all familiar with this topic, I won't spend any more time on this. Now let's go ahead and calculate the required internal forces. First, the internal forces just to the left and right of point C. Point G is taken just to the left and point H is taken just to the right of point C. I'm going to section the beam at these points, separate the beam into two parts, and consider only the left side for the analysis. And therefore, I'm only going to complete the free body diagram for the left side. We'll perform the calculations for point G on the left column here and point H on the right column here. We'll use the default directions for the X and Y axis. X is horizontal, Y is vertical. Our sign convention here is that the shear force acts vertically down on the left side, bending moment acts counterclockwise on the left side, and the axial force is tensile. In each of these cases, I wrote down three equilibrium equations for the free body diagram on the left in order to find the axial force, shear force, and the bending moment. I'll let you follow the details here. As part of understanding the basics here, I'd like to make the following observation here. We note by comparing these values with these values that number one, the axial forces calculated for the 2 points G and H are the same. The bending moments calculated for the 2 points are the same, but not the shear force. Shear force at point G is different from the shear force at point H. And we further note that if I find the difference between the two shear forces, VH minus VG, that works out to be minus 15 kilonewton. In other words, as you go across point C, the internal shear force drops by minus 15 kilonewton. This is due to the fact that there is a point load acting vertically down at point C, and the value of the point load is 15 kilonewton. And this fact will be made use of in a method that we will learn in another video. Next, let's focus on the internal forces just to the left and right of point D. Here are my analyses for those. Point I here is taken just to the left of point D, and these calculations, the calculation in the left column here, pertain to that, and point J is taken just to the right of point D, and these calculations pertain to that point. Once again, I'm considering only the left side for the analyses here. An important point to note here is that when we section the beam at point I, the externally applied moment at point D, 20 kilonewton meter, ends up on the right side. Whereas when we section the beam at point J, that external moment ends up on the left side. So that's the difference between the two free body diagrams. Once again, I'll let you follow these analyses. When we compare the results for point I and point J, what we find are these. The axial forces are the same, the shear forces are the same, but not the bending moments. If I calculate the difference between the bending moments at point J and I come up with 20 kilonewton meter, which matches exactly the externally applied moment at point D. In other words, the internal moment jumps by 20 kilonewton meter as we move across point D. And this fact will also be made use of in another method that we will learn in another video. Now let's calculate the internal forces at point F. So we go ahead and section the beam at point F, separate the beam into two parts. Like we did before, let's go ahead and use the left side to perform the analysis here. We need to complete the free body diagram for the left side, which means we need to put down all of the externally applied forces, including the reaction at point A and the part of the distributed load that's going to end up on the left side. The shape is still going to be triangle, but it's going to only extend up to this point, right up to point F. So to define this triangle, we need to find this height, y0, and that's what I'm doing over here. I'm using the principle of similar triangles to find this height right there. y0 divided by 1 meter must be equal to 10 kilonewton per meter divided by 2 meters, right? So that gives us a value of 5 kilonewton per meter for y0. Now coming back to this diagram, our free body diagram is completely defined. We find the resultant corresponding to this little triangle, which is the area of the triangle, right? So it'll be half times 1 times y0, which is 5 kilonewton per meter, and we get a value of 2.5 kilonewton for that. The resultant force F2 of 2.5 kilonewton will be acting at a distance 1/3 of 1 meter from this point, which is 0.333 meters. Now everything is fully defined for the free body diagram of the left side, so we can go ahead and apply the equilibrium equations to find the internal forces. Keep in mind that for this point, you could also use the right side to find these internal forces if you are willing to deal with this trapezoidal distributed load. Well, we'll use the left side here. Here are the calculations. We get a value of 0 for the axial force NF, a value of 9.772 kilonewton for the shear force V sub F, and a value of 13.06 kilonewton meter for the bending moment MF.